video to help you through the activities on solutions. First, let's define a solution. A solution is a homogeneous mixture of one or more components that are evenly distributed throughout the mixture. The particle size of the things in a solution are usually very, very small, so small that you can't see them and that they don't scatter light. These things are usually translucent. Iced tea is an example of a solution. Notice that in the iced tea, even though the color of the solution is dark, you can still see through it. The light will pass through the solution, and you can tell because you can see the ice cubes. A colloid is a different type of mixture. It is homogeneous because particles are evenly distributed, but the particles are a larger size. They're usually opaque mixtures. Milk is an example because milk has large enough particles that scatter light. Notice how the milk is opaque. Light doesn't travel through the milk like it does with iced tea. This is one way that you can tell something is a colloid instead of a solution. Both are homogeneous mixtures. A suspension is a heterogeneous mixture. The particles are largest in a suspension. Usually it looks very similar to a colloid when it's mixed up, but over time a suspension will settle out into different layers. Muddy water is an example of a suspension. If you mix up muddy water, you can't see through it because the particles are large and they scatter light. And it might at first look like a colloid, but you know that if you let muddy water settle, you'll get a layer of dirt at the bottom and a layer of water at the top. Blood is similar. Blood looks like a colloid because you can't see through blood. But when you centrifuge blood, or when you let blood sit for a long time, you can see that it will separate into layers. You will eventually see this in the clinic if you haven't already. In a medical setting, blood samples are normally centrifuged and the plasma is separated from the red blood cells. There's a picture of two layers of blood in the figure in front of you. The top layer is the plasma and the bottom layer are the red blood cells. The red blood cells are large compared to the other things in the solution, and they're large enough to settle out. On the other hand, the particles in milk are slightly smaller and not large enough to settle out of solution. If you haven't already, please read the material on the first page of your activity and log these definitions into your brain or put them on your cheat sheet. These are the vocabulary words that you'll want to become familiar with so that you can understand the rest of the activity. Now let's talk about solubility. Some things are more soluble than others, but in general, all solids become more soluble with increasing temperature. Or in other words, solids are normally more soluble in hot liquids than they are in cold liquids. Here's a figure to show the solubility in cold versus hot liquid. The first figure shows sugar in cold water and the same amount of sugar in the same amount of water except the water is hot. Notice that in the cold solution, light is not passing through this liquid. The particles are not completely dissolved. In this case, however, in the hot liquid, you can see straight through the solution, and it is a true solution. There's still some sugar left on the bottom because it hasn't all dissolved, but you can tell that more of the sugar has dissolved into the hot solution than in the cold solution. You can see the same sort of thing here with salt, but the temperature effect on salt is not quite as drastic as it is in sugar. Here's a chart that shows the relative solubilities of salt and sugar that vary with temperature. So here we have low temperature to high temperature, or freezing water to boiling water. So about 175 grams of sugar will dissolve in about 100 milliliters of water when the water is very cold. But that amount of sugar that can be dissolved in water drastically increases as the water gets warmer. Salt also has a very slight increase. It's increasing but not as much. And you'd have to really zoom in on this to see the increase in solubility for salt because it's so much different than sugar. The message here is that solids are more soluble in hot liquids than cold liquids, and not all solids increase their solubility with temperature at the same rate. You may be familiar with solutions that include liquids and solids, like sugar water and salt water. But did you know that gases also dissolve in liquids? Soda pop is a really good example of a liquid gas solution. All carbonated beverages have carbon dioxide dissolved in them, and that is where their fizziness comes from. If you drink soda and feel bubbles, it's the carbon dioxide coming out of solution that makes that sensation. Remember that the solubility of solids increased, or you had a positive slope for the solubility of solids in liquids, but gases actually have the opposite trend. Gases decrease their solubility as the temperature increases. Or in other words, they're more soluble in cold liquids than in hot liquids. Here's a solubility curve of carbon dioxide in water. Notice that the solubility actually decreases as the solution heats up. Think about a cold soda versus a hot soda and see if this makes sense to you. Gas solubility also depends on pressure, and this is what that psst sound is every time you open a soda. It's the pressure coming out of the can. In order to carbonate soda, it has to be sealed under pressure. So in a soda can, before you open it, there's a lot of CO2 pressure above the liquid in the can, and that forces the gas molecules to be soluble in the liquid. The higher the pressure of a gas above a liquid, the more soluble that gas is in the liquid. The higher the pressure of a gas, the more gas is actually there, and so you're pushing the gas molecules into the soda in that case. When you open a soda, you release the pressure, which is why you get fizziness. The CO2 bubbles out of the solution as the pressure is released because the CO2 is no longer quite as soluble in the liquid. Soda goes flat if it's left open because CO2 comes out of the solution after the pressure is relieved. An interesting fact is that there is actually 2 times the volume of gas dissolved in a solution of soda. Here is a cool demonstration where this person is going to put a stack of Mentos candy into a Diet Coke. When the Mentos fall into the Diet Coke, there are tiny sugar crystals on the outside of these candies that nucleate gas particles. Basically, they catalyze the gas from coming out of the soda solution. When carbon dioxide is dissolved in the liquid, it takes up a lot less space. It's part of the liquid than when it's a gas and it takes up a much larger space and it doesn't interact with other molecules. See what happens when all of the carbon dioxide in the soda suddenly turns into gas. The volume of the gas is too big for the container, and so it pushes the gas and the soda out of the container very quickly. And you get a soda geyser. If you try this at home, please be careful and make sure you wear safety glasses. Now you know how the pressure of a gas affects its solubility. Let's talk about how this plays into our breathing. When you inhale air into your lungs, the pressure of oxygen in the air is 160 millimeters of mercury, and the pressure of carbon dioxide in that air is 0.3 millimeters of mercury. So notice that there is a lot more oxygen in the air that we breathe than there is carbon dioxide. This is important for how our bodies function. If there is deoxygenated blood coming into the lungs, the pressure of oxygen in the blood from the dissolved oxygen is 40 millimeters of mercury. Let's focus only on the oxygen right now. So as the blood is coming to the lungs, there's a low pressure of oxygen in the blood compared to in the lungs. Gases will always move from a higher pressure to a lower pressure. Therefore, the oxygen in the lungs at 160 millimeters of mercury will move into the blood, which is at a lower pressure of oxygen. This enriches the blood in oxygen and leaves it at about 95 millimeters of mercury. Then this oxygenated blood reaches the tissues and cells of your body. The pressure of the oxygen in this oxygenated blood is 95 millimeters of mercury, but your cells are using oxygen, and so any oxygen that comes in here is used up. The pressure of oxygen in your cells and tissues is around 20 millimeters of mercury. Notice that this pressure is lower than the pressure of oxygen in the oxygen-rich blood. Because of this, oxygen will move out of the bloodstream through vascular membranes and into cells and tissues. The cells will end up using that oxygen content and producing carbon dioxide. When oxygen moves out of the blood, the pressure of oxygen drops from 95 back to 40, and this cycle happens over and over again. Now let's focus on the carbon dioxide. Let's start here. Notice that the pressure of carbon dioxide, which is being produced by cells as a byproduct of metabolism, is 46 millimeters of mercury. This is slightly higher than the pressure of carbon dioxide in the oxygen-rich blood. So what will happen there? The carbon dioxide in the blood is low, and in the cells is high. It will move from the high pressure to the low pressure. This will increase the pressure of carbon dioxide in the blood from 40 to around 45 millimeters of mercury. Now this blood enters the lungs. In the lungs, the pressure of carbon dioxide is very low because there's a low pressure of carbon dioxide in the atmosphere. The high concentration or the high pressure in the blood will be released by carbon dioxide passing out of the blood into the lungs. The carbon dioxide is then exhaled and your fresh air is inhaled. This cycle starts all over again. The exhalation of carbon dioxide lowers the pressure from 45 to 40. Pressure is directly related to concentration. So this is also like saying there's a lower concentration of carbon dioxide here and a higher concentration of carbon dioxide here. Okay, now let's talk about electrolytes. All of you know that tap water conducts electricity, and that's why you've seen a tag like this on your hairdryer. Let's talk about the conductivity of water and electrolyte solutions. In front of me, I have 4 beakers of water. 3 of these beakers have deionized or distilled water, and 1 of them has tap water. I'm not sure which one's which. So let's see if we can find out. I've also got a light bulb here. And this light bulb is not making a complete circuit. I would have to touch these 2 pieces of metal together in order to get the light bulb to light. Or I would have to connect them in some way that conducts electricity. I'm going to sit my light bulb here. And I'm going to plug in this light bulb and try not to electrocute myself. Okay, the light bulb is plugged in. Now my biggest job is not to electrocute myself. Let's stick the ends of these 2 wires into one of these beakers. Do you see how the light bulb is barely lit? This is tap water. Let's try it in another beaker. It's not lighting at all. The difference between these 2 beakers is that one is tap water and one is deionized water. The tap water is full of electrolytes, or it's full of ions. You may know that in South Bend, Indiana, we have pretty hard water. It's full of ions, and it's the ions that allow the conduction of electricity. In distilled water, we don't have ions. It's sometimes called deionized water because all of the ions have been removed. Therefore, it won't conduct electricity. Now, the reason that you have to be careful of a hairdryer in bath water is because the bath water is tap water, and you've also probably added other things to it like soap. All right, so now let's talk about how to make these water solutions conduct electricity. If I add an electrolyte, something like sodium chloride, which is ionic, I will end up getting positive and negative charged ions in solution. These are the things that conduct electricity. Let me remind you that this beaker is not conducting electricity because it's pure water and it doesn't have any ions. All of the electrons are in covalent bonds, and so electrons can't jump from one wire to the other. If there were ions in solution, though, the ions can conduct electricity. Electrons can jump from the chlorines to the sodium and conduct electricity. Let's try adding salt to this solution. I'm just going to add a little bit. And I'll stir it up. And let's see what happens. Wow, that's really bright. So this solution now is conducting electricity because it has ions in it. And electrons can flow from one ion to another because the electrons are not caught up in covalent bonds. Now let's look at something like sugar. Sugar is not an ionic compound. It is polar and it is going to dissolve in water, but it's not an ionic compound. So When you dissolve sugar in water, the sugar does hydrogen bond, but it doesn't form ions in solution. Let's see what happens. Here's another container of distilled water. Notice that it's not conducting electricity because it doesn't have any ions in it. Now, what if I put an entire packet of Dunkin' Donuts sugar into this beaker? It's almost all dissolved. All right. Now remember, when I put just a little bit of salt, I got this kind of effect. I'm going to rinse this off. And now if I put it in here, where the sugar water is, I still don't get any conductivity. This is because sugar does not form ions in solution, and so it's not an electrolyte. When I put sodium chloride into water, every single one of the sodium chloride units breaks up into sodium ions and chloride ions. This is complete dissociation into ions, and this is called a strong electrolyte. Something that does not dissociate into ions is called a non-electrolyte. Its solutions do not conduct electricity. There's one more category that I would like you to know about. Know that carboxylic acids and amines are weak acids and bases, and weak acids and bases are weak electrolytes. If I put a carboxylic acid into a solution, some of the carboxylic acids will dissociate and form carboxylates and protons, but not all of them. They will partially dissociate, which means that some of them will dissociate and some of them won't. Only about 10%, for example, might actually dissociate and go through the reaction that's written here. Let's do an example. Here I have glacial acetic acid. And I have one last beaker of deionized water. The deionized water does not conduct electricity. I will add a nice big squirt of the glacial acetic acid. Oh, it stinks. It smells like vinegar. I've stirred it up, and now I will put my light bulb into this solution. Can you see that the light bulb is slightly lighting up? It's not very bright, but it is conducting some electricity because it's making some ions in solution, but not very many. This is called a weak electrolyte because it makes some ions in solution, but not very many. Carboxylic acids and amines are two things that you should be familiar with, and remember that they become weak electrolytes when dissolved in water. Thanks for watching this video on solutions. Please complete the activity, and if you have any questions, feel free to post them in the comments. If you found this video helpful, please let me know by giving me a vote.